Live stream running. We should have some pretty crazy stuff going on. I don't know. You guys can see over here. We'll zoom. You'll get to see it in a minute. All right. Before we go on, I don't like preaching to you. I don't like kind of, giving you like, oh, you need to do this, you need to do that. But I want to say a couple of things really quick, because this is pretty much, in my opinion, the last time I could say something before test one and have any hope of you actually listening and having time to do something about it. So let's think big picture here. Why are you forced to take physics? Some of you are physics majors, some of you are engineers. There's a couple of main reasons why you're here. One, time management. When you take a physics class, you are forced to be good at time management. This is why other disciplines want you to do this. One of the reasons. You are also forced to read carefully, right? Every word, every minus sign has a meaning, and it forces you to increase your precision of language. And the third one, which is probably more true than any of them, and I don't know, I don't like using buzzwords, but here it is, grit. Learning the ability to suffer and do things you don't want to do so that you can meet a deadline. That's probably the biggest reason you have to take this for all these classes that you think this means nothing to me. Now, learning to read technical content is a huge thing, right? Being forced to look at equations or read books and do critical understanding on tough technical information is another big feature, right? So, and again, getting stuff done, turning things in on a deadline. Now, that's why we're in here, most of us. I have another question for you. If I could tell you a secret about physics that would ensure you could get 10% higher scores or more on every single physics exam you ever take, you would probably want to know that information, right? 10% boost on every test, right? Am I right? Here it is. Master chapter 1 and 3. And graphs. That's not a very good secret. But I'll tell you something about me as an instructor. Every single test, I usually have at least one graphing question. Alan, am I lying? Nope. Every single test, I usually have a question about vectors. Is that true? Yep. And pretty much every single test, there's a check the units question, or you have to deal with units and prefixes, right? This happens. So imagine you have to take 3 midterms and a final. Then you have to do it again. That's 8 exams. If you had to pick one time to just suck it up, have no social life, and really be good at some stuff, this is that time, this nice holiday weekend, because it's an investment in your future. You won't have to be struggling with these concepts on every single exam if you master them now. If you don't master them, you're just going to hurt over and over and over again. So is that enough said? A little side note, I happen to know there's a question on your test that is going to require the quadratic formula, and I don't want any surprises. If you haven't seen any of the homework that requires a quadratic formula, you probably better do a little quadratic formula practice so you're not rusty on that. You know what I'm saying? So maybe there's a way you could work around it, but I think, and that's true on all 4 versions of the test. That's right, 4 versions, right? So you're not, everybody's getting different versions, so just be aware. And they're not just subtle things like changing the numbers. It's literally changing the figures and making unique problems. So you're gonna have a hard time cheating your way through this class. So you just gotta suck it up and master this. Is that enough on that? Vectors, graphs, units, we use it all the time. Prefixes. You do not want to be fooling around. Make sure you're expert at that. And this is the time. The other thing is the exam is 228, right? That's the money. Okay. You're going to get practice tests. I know I come off as being tough, right? But I want you to think about this. There's not a lot of classes where your teacher literally writes every single homework question, every single solution, 4 practice tests, 4 full color solutions. And yeah, and I gave you a study guide on the test. So it's like, I know it's tough. Life isn't fair. We know this, right? The world is geared towards rich people. They've got it made. You do not. You would not be here if you were loaded. So we know the world isn't fair. I'm trying to do my best. I'm trying to keep costs low and keep the solutions out there so you can do it at your schedule, right? It's not fun when you have to choose between driving to school and having gas or dinner. That's not cool, right? So I appreciate that some of you have a lot of odds against you. So I've tried to make it so that you can practice whenever you want. When you take the practice test, 1, time yourself. Okay. Number 2, actually don't use the solutions. Whoops, how about this? No solutions during the practice, right? Treat it like a real test. The more you treat the practice test like a real test, the higher probability you have of being comfortable during the real test. I give you those practice tests so that you can then grade yourself afterwards. Or I give you the solutions to these tests so you can grade afterwards. And actually look at them. Don't be, I've had students say, oh, I'm pretty sure I got that right. And I walk up, you realize that's completely wrong. Oh, really? I had a student that wouldn't even look at the solutions. He was like, I think I got that right. What are you going to do? So grade it afterwards and grade yourself tough. All right. And then what will happen is, oh, I must just do this. Do at least 3. Okay, the odds are stacked against you. We've been in COVID learning. You know your chops are not what they should be if you've been checking all the time. So let's be real about this, right? You've been able to cruise and things have been easy. This is not that time anymore. This is like full punched in the face, horrible physics test. Now, hopefully you'll find that if you do this by the 3rd practice test, or maybe the 4th, you'll rock this class. But if you just do 1 practice test, there's so many questions to choose from, and I only put about, I think, 10 on each test. It's very likely the ones that you practice on the first practice test might not be there. Some of them might be, some of them won't be, right? So, right, if you only do 1 practice test, you're not going to be prepared. If you do 2, you'll maybe get a D. If you do 3 or more, you'll probably get a C or a B, right? There's some like exponential ramp up on the 3rd test. It really kicks in. Enough said? All right. And after the first test, I'm not going to say this anymore because after the first test, it's too late. Right? If you don't study your ass off for the first test, you set yourself back. It's really hard to dig yourself out of a hole. I think I've had 2 students in my entire, oh my gosh, 17 years or something here. I forget how long I've been here, something like that. Isn't that crazy? 17 years. But I've had students twice that dug themselves out of a really deep hole, right? You don't want to get in the deep hole on test 1. And to be clear, if you had me during COVID times, full COVID, just forget that experience because we know that was total nonsense and it was not reflective of real physics class. But now we're in a real physics class, right? We're actually able to take paper exams instead of quizzes where you got 0 partial credit. So if you're like demoralized from having to, take this class again because of COVID, just try to put that out of your mind. That was a horrible class. All right. What do you think? You ready to do some forces? Let's do it. Oh yeah, another thing, you may want to get the volume 2 soon because of supply chain problems. If you don't order it today off Amazon, it might not be here for 2 weeks. Crazy. I'll remind you of that next time. Page 83. Now, there's a lot of notes on here, so hopefully you don't have to write down them. You just kind of pay attention. You got the live stream too. Okay, so forces. I want you to, when I say a force, I want you to think about the word push and pull. Like you push or pull on something, that's when you're exerting a force, okay? When you push or pull, that's when you exert a force. Some of the most common forces we're going to have are a normal force, a frictional force, a tension force, and these are all on page 83. And what else? Maybe we'll just have arbitrary F. Was there another one I want to do? Oh, weight force. Now these are force vectors. This is the normal force vector. This is the normal force magnitude. So a lot of times what's going to happen is technically forces are vectors and should have arrows over them. So this would be friction, this would be tension, and this would be weight. Now, these are the most common forces we're going to encounter, and we're going to focus on friction in chapter 6, the next chapter, but I'm including it here just for completeness. To be clear, in our pictures, we oftentimes just write the magnitude. And this, capital T, would be the tension mag. And finally here, what's an equation we oftentimes use for the magnitude of weight? Does anybody happen to remember? mg, excellent. So notice this one's a little bit different. Maybe you say, oh, the weight is mg, the weight is mg. Technically, that's the weight magnitude. Okay, the weight magnitude. These are the most common. There's many other forces in here. We'll get to them in time. We'll talk about magnetic forces or electrical forces later on. In chapter 13, we can talk about a different type of gravitational force that's similar to weight, but it's applicable for planets. So we call that the universal gravitation force. Maybe we should talk about units really quick. Just a reminder, does anybody know the units of force? Newtons. What's 1 Newton?
1 kilogram times meter over second squared.
Yes. Now, here's my way of remembering it. A weight is like an mg, right? Think about this. Weight is a force. This is the magnitude of weight. mg. Notice the units kind of match up. So I like to think the units of force are the units of mg. That just helps me remember. So far, so good? And hopefully, most of this is still review from high school physics, but I'll point out something else that some of you may have done. And let me just get a little bit here. Oops. In a lot of classes, maybe in high school or something, or maybe in other textbooks, sometimes you'll see this written as force subscript n. I don't like to do that because we're going to have enough subscripts already. So in my solutions, just to be clear, if you did this kind of stuff on a test because you're used to it, I'm not going to grade you down for writing it this way. Okay. Sometimes people like to write force subscript tension, and maybe this would be force subscript weight or something like that. This is not wrong. I just prefer these because that's how I happen to choose to write my solutions. Notice something that the way I like requires. There's a big difference between lowercase n and uppercase n. Uppercase n is the unit of force, newtons. Lowercase n is the magnitude of the normal force. So far, so good? Just helping you know the way I write things. Everybody know what normal means in mathematics? It actually has an official meaning in mathematics. It's actually useful for us. Normal means perpendicular. Yeah, maybe you've heard of orthonormal basis sets, or perhaps you've heard of the unit binormal in some weird calculus class. So just so you know, I'm going to write this symbol, perpendicular. And in particular, it's perpendicular to a surface. For example, when I hit this book on my head, it's pushing me, and it's pushing in a direction perpendicular to its surface, right? So if I angle this, the normal force is perpendicular to the surface here. Whoops. Let me try and do it with the other hand. Right, the idea is it's normal, and so the normal force, you can kind of remember normal means perpendicular in math, so the normal force is perpendicular to this surface. That's a tip I like to remember. Oh, uppercase T means tension. What's lowercase t, usually for our class? So this is, we're already used to having to keep track of this, so just be aware, capital T is tension, lowercase t is going to mean time for this class. So far, so good? All right. Good enough. Give me a second. Does anybody know Newton's laws? Maybe you heard them in high school, or maybe you heard a story about them in a, you know, maybe you are familiar with them. For example, does anybody know Newton's first law? And I could call that N1L. Does anybody have that in your mind? What do you know of Newton's first law? Anybody? It's okay if you don't remember.
Stays at rest.
Object at rest, stays at rest. Okay, sure. So we're talking object at rest stays. You don't need to write this down. It's at the top of the next page, but don't look yet. Okay. Unless there's a key word that I was looking for. Unless net external force. And most people know object at rest stays at rest. But it's crucial that you add in unless there's an external force. Okay. What's the next line of this phrase usually? Object in motion stays in motion. Exactly. Nice. Unless the same words apply. Okay, got it? That's Newton's second law, or what's first law? I don't like to spend a lot of time on it. Basically, we say this. I don't know if you're familiar with this. That's Newton's first law. Now, maybe you haven't used this symbol in a while. Maybe you didn't take a calc class recently. This means sum of, as in addition of all of them, not just some of them. Right? So in this case, if you take all of the external forces and you add them up, if they equal 0, you have no acceleration. Now think about this. If you were at rest and your acceleration is 0, you would stay at rest. If you're in motion and you have no acceleration, you would stay in motion, right? Acceleration relates to the change in your motional state. A long time ago, maybe it was Galileo or somebody, thought force directly related to motion and velocity. And it turns out that was not right. A lot of people think you need force to have motion. That is not true. You need force to change your motional state. Got it? If something's moving, you need a force to stop it. If something's stopped, you need a force to start it. But you don't need force to keep moving in a straight line. All right, so far so good. What's Newton's second law? Anybody have that? I wouldn't go that way. Nope. We'll call this N2L. What's if you had to know one equation from high school physics, what's the one equation you always said all the time?
F equals MA.
That's it. Now we're going to soup this up a little bit. We're going to make these vectors. And really what I mean is the net force. So the net force. Now, to be clear, sometimes we'll literally write this as force net, meaning the sum of all the forces. Do you agree Newton's first law is essentially the same as Newton's second law with A set to 0? So most of the time, we never actually use Newton's first law. We'll just use Newton's second all the time and set A to 0. That way we don't have to remember two laws. When Newton first wrote it, I believe it was written this way. And I think this has some merit in discussing. Net force on an object divided by its mass gives you its acceleration. If you have a force and it's really big, but the mass is enormous, a big force will cause almost no acceleration. So this is kind of a visceral way to think about it, right? Acceleration is dv dt, right? The change in velocity. So the net force will change your velocity. So far, so good? All right. And then what's Newton's third law? Anybody? Action, reaction. This is the most commonly misunderstood one. I'm going to spend time on this in next lecture, but I wanted to have it here for completion. Every action has an equal and opposite reaction. Now, in this class, in theory, you've had some kind of physics at some point. So I'm going to throw something out here. Let's say we have a block, and it's sitting on a table. Okay. Now, I know we haven't discussed free body diagrams, but I'm going to draw one. What is one force that acts on a block when it's sitting on a table? Gravity. The magnitude of that is mg. And if you don't understand this, we're going to pick it up later. What is holding up the block? What type of force do you think this is? Is it a tension from a strain? It's a normal force that's perpendicular to the surface. In this case, let's say it's sitting there at rest. So I'm going to draw a little coordinate system here, x and y. And I'm going to say the acceleration is equal to 0. Okay. The name for this force, technically, mg with this direction together, that's the weight force. So I'm just going to say it's the weight vector. The weight vector is mg with that direction. Right? Up here, we have a normal force. And I'm going to call it normal with a vector. Well, what is, okay, let's say the weight force is the action. What is the reaction force? What is the force that is equal and opposite? What's that? That's what you think, and it's completely wrong. And it's what almost everybody hears as a kid. It's total lies, nonsense. Now here's the thing. You'd be like, wait, look, this force is equal in size and opposite in direction. I agree. That doesn't mean it's the action-reaction pair. Just because something is equal and opposite does not make it an action-reaction pair. In fact, what object is pulling the block downwards using gravity? What thing? What is it?
The Earth.
The Earth pulls the block down using gravity. That's what the weight force is. The opposite of that is the block pulls the Earth upwards using gravity. You don't like it. It may not feel comfortable. We don't notice it because the Earth's mass is so big. We don't notice the Earth. When I jump up, you don't see the Earth coming up to meet me. It is. It's just only moving a billionth of a radius of an atom. Anyways, it's very confusing for students. Just because these things are equal and opposite, we're going to spend time on that later, and I'll clarify that more in my next lecture. So far, so good? All right. If I could say one more thing about these. This is basically the law of inertia. And inertia in physics means mass. Right? You can think of these all together as having some sort of concept of inertia and mass. In particular, we're looking right here. The more mass you have, the more you resist changes in motion. Again, the bigger m is, the smaller dv dt is. The bigger mass, less change in your motion. So far, so good? All right. Let's try and do this. Okay, so take a look at the top of page 84. Notice I talk about Newton's first law and second law there. And I usually don't even talk about the third law. If you care, the third law, if you want to make a note about it, the third law gets its own full page on page 88. So if you're curious, if you want to make a comment, you could put N3L, page 88. We're going to come back to Newton's third law next time. All right, so now, oops, wrong way. All right, we're looking at the back of your head. Yeah, so you want to help me out? You want to just come up? All right, and so look at this problem. Take a second and look at problem 5.1 in your workbook. Talk with your neighbors. And we can talk here as well. We'll three be here. Yeah, so we got these two masses. Here's the idea. On one of them, you're going to pull really slow. If you got to stand over here while you do it. You can see, Brian, you're going to pull this first one really slow. And the second one, you're going to pull it really fast. And the question we have is, which string will break? Will they both break? Will only the top or only the bottom? Go ahead and discuss with Pete for a second. So just so the mic can pick that up, right? We're basically going to pull on the strings. And so in one case, we're going to pull really slowly. In the other case, we're going to pull super fast. Which strings are going to break? You guys think while I erase the board and get ready?
I think that's because this actually did happen to me once at home. Because like I have the floating string. I have this thing that I broke the string. Oh, I broke the string of it. I was like, oh, that's not good.
I think the max is gonna, the bottom's gonna break, the max is gonna float up.
This thing, which term will break?
Yeah.
It wasn't like I was yanking hard. Like, I was just casually pulling it just to turn off the light. And then the fans just started going crazy. But of course, I had to reattach it somehow. It worked.
Actually, it already has the same. I mean, I guess this
That's more tension.
All right. Hopefully you've had a second to think about it. So let's do this. Switch spots with me. So what do you think, class? This first one is going to pull very slowly. It's okay to be wrong. Just take a guess. Which string do you think will break? The top one or the bottom one with a slow pull? Okay, let's find out. Do it. Pull nice and slow. Try and pull straight down. Yeah, you can just wrap it around. Like I kind of do this too. Check this out. I'll just like literally grab it like this. Wrap it around my hand and slowly pull down. And then it'll hopefully not smash your hand too bad. Got it?
You already said
Slow pull. Which one broke? The top one. Okay, now this one, you got to be aggressive. Just go bam.
Just really fast.
Just pop it hard. Oh, let's try it again. Try this. Just grab this bottom mass and just pop it super hard. Yeah, you got to go as hard as you can. Notice when he pulls it as hard as he can, the top one stays in place. Let's give him a round of applause. So what's going on there? In this case, with the slow pull, as you increase the force here, right, there's the mass here, and this tension has to support not only the weight of this mass, but also the extra amount you're pulling. But when you pull quickly, why doesn't it do the same thing? Well, I claim this. If he used a big mass there, right, if he pulls very quickly, this mass will not have much time to accelerate. If this mass doesn't accelerate very rapidly, it's not going to move very much. If it doesn't move very much, this string is not going to stretch very much and it's not going to snap. So we see this is supposed to be a demonstration of inertia. Now I need someone who's ready to smash something with a baseball bat. You ready? Let's go. Give me a sec. Take a look at the next comment. See the broomstick on 2 wine glasses in your book? Okay. So you can read about that or you can just watch over here. Now, you got to be really aggressive, all right? And we probably need safety glasses, which we've got some down here. Ratings and anybody in this first, all of you need safety. So, yeah. In case. Here, you know what? Blindness is not cool. Okay. Better to have safety than not, right?
Are we all getting one?
Yeah, that's right. I'll leave these back and let that. Yeah. All right. You guys, okay, so you're probably good in that last row. Now here's the deal. All right. Real wine here, right? It's up my sleeve. You can see the giant mess from earlier. You gotta watch carefully. We took a couple of pins. With the heads of these pins. Really delicate demo. Do you agree this is barely balanced on here? Now, he's going to come over here and swing that baseball bat as hard as he freaking can. You got to be aggressive. And when you do this, you got to be careful. I want you to watch. Sometimes it will break the stick, and then you got to watch between. That's good. Let's just do it. Let's give him a 3 count. So I'm going to do 1, 2, 3, smash. Yep. You got safeties? I do safeties. Okay, ready? We'll explain it later. Okay. Let's give it a 3 count. So 1, 2, 3, smash. 1, 2, 3. Let's give him a round of applause. That's cool. What is the principle behind this? Hey, Angus, out here. Angus puts a lot of work setting this stuff up for you. Let's give him a round of applause. Yeah, it was pretty smooth. Would you say that was an awesome smash?
Yeah.
Now, so the idea here is, why is this demo actually related to what we're talking about? Because he smashed this thing so fast, the time it takes the shock wave to travel down to the end is longer than the time it takes it to smash the stick. As a result, these don't pull these down and tip them all over, right? So that's why the wine glasses don't tip over and break. That's a nice backup, just in case you use plastic glasses. Anyways, so that's a nice backup. All right, so far so good? I got one more. One more. I need another volunteer. Who's ready? Somebody different, maybe. This one, you don't have to smash anything. Well, oh, are you volunteering? All right, we got to volunteer. Okay, so you two, wait, no. You two are in the shot, so scoot that way. Is that cool? Yeah, because we're going right here. So we're talking about the tablecloth trick 5.2. So I'm going to teach you how to do this. All right, so I'm going to show you once and then I'm going to have you do it, right? So the idea here is you want to pull this out and make sure your head's not in the shot. You're good. You're good. Okay. You're like barely at the edge of the frame. So if you scoot that way, it's 3 inches. So the trick is if you pull this thing and you lift up, all the blocks are going to fall off. Furthermore, we got a nice smooth tablecloth. We got no seams here. What you can do is you can use the edge of the table as a pulley, and if you pull straight down, the tablecloth should come straight out. And you got to grab it here, and you got to kind of crouch and get into it and pull it really fast. I think you can do that.
I can try it.
All right, let's make it a little bit more interesting. Hold on.
No.
Oh. There's a lot more fiber in your diet, right? Why am I stacking these blocks of wood on the table, on the plate?
More math.
More mass. Don't screw this up. What's the trick? Before you do this, don't do it. Don't forget. What's the trick? Remind me. Get low, pull straight down, and you got to hit it hard. Ready? Let's give him a 3 count. Ready? 1, 2, 3, go! Go aggressive. Go get it. Yeah, let's give him an applause. No, that was pretty good. You got all the hard stuff. That's what matters, right? Yeah, it's tricky because you have to have a full leg to travel to get it out. You probably hit the ground, right? Yeah. All right, that was pretty good. Again, lots of mass, lots of inertia. Do these objects stay at rest? No. They accelerate such a tiny amount you don't see it. So it looks like they stay at rest. Look at the very bottom of the page now. Read the bottom of the page. The bottom of page 84 tells you some physics about all that. Well, I get set up for the next demo or the next thing. It's all about force versus time, right? If you pull quickly, the amount of acceleration it's basically this right here. There's lots of mass, so the acceleration is tiny. It's not 0, but it's tiny. And if you pull quickly, you have a tiny acceleration for a tiny amount of time. It doesn't move much and you don't notice the motion. But if you watch that in slow-mo, if you watch it in super slow-mo, you might see it move a millimeter or 2. If you really, really cared, somewhere I did this problem more detailed. I don't remember where. I'll tell you later. Okay? Let's worry about it later. Next, we want to understand free body diagrams. Okay, so if we want to do force problems, you probably did this in high school. We want to make sure you're doing high quality free body diagrams, or maybe in physics 110. And in particular, every teacher is a little different, but there's a couple of things you can do to improve your ability to communicate your knowledge of the subject with your instructor. I should tell you one other thing. To be clear, test 1 is covering chapters 1 through 4. This is chapter 5. So we got to keep rolling through the class. Just so you know, this stuff is going to be on test 2. But, right, I'm trying to make sure you have plenty of time to study. I already preached at you. I'm not going to do that anymore. Okay, we got to keep cruising. All right, let's look at 5.3. Is this a ball hanging there? Oh, it's a ball. we're going to try and learn about scale. And I encourage you to ask any questions you have that are confusing. But to help you, scale. One of the hard parts about physics is you have to break people of all their bad habits that they've learned from watching TV for 20 years, right? What does a scale read? What does it say it? The gravitational, I couldn't hear you.
Force downwards.
That's a good guess, but that's not true. What is the name for the gravitational force acting on this? I'll wait for it. Weight, right? Okay, the weight of this. If this, do you agree the weight of this is the same whether I move it around or not? It's near the planet Earth. Now, if we go up into outer space, that would be different, but near the planet, do you agree your weight doesn't change when you move around? Well, my claim is the scale reading does move around. You agree the scale reading is not reading the weight of this object right now. It's all over the place. Scale doesn't read weight. At this point, the scale reading is equal to the weight force magnitude, but it's actually reading tension. Okay, so it's a lot like that last problem. In this case, I'm going to draw a free body diagram. This is our first thing we just learned. Scales, I'll call this a spring scale. And in fact, I'll call it a hanging spring scale. It records tension, not the weight. Usually, well, we'll discuss this in a minute. In this particular example, I believe I drew a coordinate system here like this. X and Y. And which was this thing accelerating downwards with magnitude A?
Yep.
So this is accelerating downwards with magnitude A. A is a positive number. The direction is downwards. The coordinate system, upwards, is positive. Okay. So here is an FBD. We're going to do an FBD of the ball, or whatever's hanging on there, okay? I've got a coordinate system. You have to have that, but I don't want the coordinate system touching the object. Here's my object. What is one force acting on the ball? What's that? Tension. Which way? Okay, let's not overthink it. There's tension up. Now, to be clear, together, these two things are the tension vector. Agreed? There's the magnitude and the direction. All right, next. What's another force?
mg downward.
mg. Downwards. Now, I could try to write down this sum of forces equation. I'm going to remind us of Newton's second law. Sum of force net equals mass times acceleration. That's Newton's second law. N2L. In this equation, these come from the arrows on object in what's called the FBD. FBD means free body diagram. It does not mean forced body diagram, but I get your idea there. Free body diagram, FBD. So far, so good? Notice this is a vector equation. You know how I've been harping on the independence of X and Y motion, blah, 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 blah. That's also true here. We can split this into an X equation and a Y equation. So usually we'll do sum of forces in the X equal mass times acceleration in the X. sum of forces in the y equal mass times acceleration in the y. So far, so good? Are there any forces left, right? Are there any forces that match the x coordinate? No. Well, gee, I wonder what we're going to find out. There's no forces here. What's the acceleration? Shocking. If there's no forces, there's no acceleration. Woo! Okay, let's try the y direction. Give me one force in the y direction. Okay, gravity. Is gravity positive or negative in this picture with this coordinate system? Negative. mg is opposite the coordinate. Negative mg. Okay. What's the other one? Positive or negative according to this coordinate? Positive. Equal to mass. In this case, I'm just going to write AY. What is AY for this problem?
Negative 2.
It's not negative G. Negative G is only true if it's in free fall. This is attached to an elevator. Hopefully the elevator is not in free fall. That would be a pretty cool ride for about half a second. Okay, so what else is it? What did the coordinate system tell us here? Negative A. Yeah. A lot of people think force equals MA and forget about the minus sign. Remember, I've been trying to harp on this as well. The sign that you assign this parameter depends on the relative directions of the arrow and the coordinate system. So for this weird ass problem, we should do negative A. Keep in mind, what does A mean? The magnitude. So the negative sign is what we call explicit, explicitly shown. If you solved for these parameters, A should be a positive number because then we'd expect like 6 downwards or something like that. All right. So in this case, I'm just going to rearrange this and solve for the tension. You could do it as well. Ratio. Solve for T. Just to clarify this, I'm going to put this right here. Did you get this? T is mg minus ma. Now let's think. There's a student that said the tension equals the weight. Do you agree that's, or the scale reading is the weight? Do you agree that's going to be true in certain cases, but not all? If A, well, let me ask you this. Under what circumstances does the tension read the true weight? When A is 0. So that's, and this is the thing, most of us do not use scales on elevators when we're riding around, all right? So it's, yeah, I get the idea. This is why we usually say the scale reads your weight. But technically it reads either a normal force or a tension. All right, whatever. All right, I've got another question for you. What if there was a comment about an elevator dropping, right? What if we were in an elevator and we were falling? Right, what if I would, let's say we all go in the elevator, huff each other's COVID breath, and then cut the cable. We cut the cable in the elevator, and instead of thinking about COVID, we watch a scale. What do you think the scale would read if we're all inside the elevator that's falling down? What would the acceleration be if you cut the cable? What will be the magnitude of your downwards acceleration if you're in free fall? G. Not the force, it's an acceleration, so it'd be G, which relates to the force. So that's a case, what if A was equal to G, what does the scale read? Could we possibly test that? Okay, and of course, this probably won't show up, but, right? This is a 1 kilogram mass. What's 1 kilogram times 9.8 meters per second squared? 10, about 10 newtons. So, right, just kind of look here. This is a 1 kilogram. Do you agree the scale's not lying to you? It's about 10. The reason it's wiggling is I had 3 cups of coffee. Now I'm going to drop it into this bucket. Watch the scale. You can always watch this video later on YouTube at quarter speed. You can see the scale instantaneously drop to 0 for a split second.
Yes.
So this is an attempt to verify that. When you're at rest, the tension reads the true weight. When you're falling down in free fall, we see the scale reads 0. Scales do not read your weight. They read the tension in the spring. Good enough? What do you think? Is this all pretty good review for most of you? Have thumbs up, thumbs down? Just let me kind of read the room here. Okay. Now, I want to point out a logical question might be, why don't you just flip the coordinate system upside down? Look at the next problem. If you flip the coordinate system, what's going to happen? Well, let's just look at that really quick. Let's go to the other board. So we're looking at 5.4. Right? In this case, you're standing on a scale in the elevator. And the elevator is accelerating down, but we flip our coordinate system. In this case, if you're standing on the scale, is it a tension force or is it some other kind of force if you stand on it? Or the normal force. So our FBD might look something like this. A normal force up, what force was down? mg. What would the force equation read? In this case, let's just do some, and I think I said this was x, this was y. If we do the sum of forces in the y direction, because we know the x is boring, what do you get for the sum of forces in the y using this coordinate system? mg right? So far, so good. And then just for a second here. I want to compare. Oh, geez. Oh my gosh. All right, I want to compare this equation, which used this coordinate system, to this equation using that coordinate system. Notice these equations are essentially identical. Now, wait, we changed the letter T to N because we changed the type of scale, right? And then look, everything in here is negative, agreed? When you flip the coordinate system, everything goes negative compared to this one. One of the tricks I use in it, and you may be saying, why would you ever flip this? It turns out this is one of the common tricks physicists use all the time to reduce the amount of work. We change our coordinate systems to make it easier to write some equations. Right now, it's maybe not obvious. But when we're moving in circles and when we're going on ramps, sometimes we're going to want to change our coordinate system. So that's why I'm spending time on this. The trick that I like to do is I look at the force arrows that match the acceleration arrows. These two have the same sign. What do I put for AY? In this one, positive A, right? Look, in this case, A is matching the direction of the coordinate system. Now look over here in this one. Whoops. These two have the same sign. See it? Feeling good? That's my way of checking my work. I look at the acceleration arrows and I look at one of the force arrows that matches its direction. I know that I wrote the force equation correctly if the force that's downwards matches the acceleration that's downwards. Or in some other problem, if the acceleration was upwards, then it should match the sign of tension. Good? What do you think? You want to take a break? Is this a good time, or do you want to keep pushing through? You want to just do physics till midnight? How about we take a break? All right, we'll come back and do some more problems. Feels like the brakes are too short, right?
Or unless they go by too fast.
All right, let's do.
The acceleration is zero.
I have a fun one for you here, real quick. Look at 5.5 really quick. All right? To help you visualize this. Oh. You got 5.5. Oh. Okay. Up here I have a scale. Hopefully this will not hit the ground. You see those masses are hanging off the ground there? Oops, you can't see it on Zoom. Then you can.
I think I might move.
Oh, you don't need to make much for this one. This is kind of cheap. Just the back up for your sake. Okay, nothing on my sleeve here, right? You agree there's definitely plenty of room under here. These masses are suspended. So the question 5.5 is simple. I've got two 1 kilogram masses here. I've got a scale here, and my question is, oops, I have to turn the scale on with no weight on it. So let me take these back off. Hold on. Okay, now there's basically no tension in the string. Agreed?
Yeah.
Let me do this. Let me really make sure. Okay, so now there's definitely no tension in the string. Okay, now this is a weird scale. I know you can't really see it that well. I'll have to zoom in on it when it reads. It should read 0 right now, but it's actually in units of kilograms, which makes no sense because it's not a force. But do you agree we could take the kilograms and multiply by 9.8 to get to newtons? So in this case, now what I want to do is I want to hang these two masses from there. What do you think the scale is going to read? In particular, let's think about one side of this, right? This is about 10 newtons. There's 10 newtons of weight. What's the tension in this string right now, right here? 10 newtons because it's balanced. Similarly, Alan, am I still on Zoom?
Yeah.
Okay. This one, 10 newtons here and here. When I hang them, what do you think the scale is going to read? 10, 20, or 5? Discuss with your neighbor real quick. That's what I'm asking. Yeah.
The reaction thing. It's the same force. Whatever. I think we make this one.
Oh, yeah. Is it like the scale, like?
So you could be looking at the action.
Action or 5. If it was 0, that would be pretty.
Or could it be 0? I don't know.
I think it was 0.
The thing that unsells me is that unnecessary slab on the bottom. No, because like notice the left side how there's not a small slab. That's just my
It would be 10 each. Yeah, so I think that
No, but if they're both
unless it
float,
does
there
opposite.
should
Oh, yeah, I think it's.
because like of course because they consider the string as well. Like the string is tensed up.
I don't know. Until major stuff.
Always trying to trick you, right? Okay. What's your gut tell you? Did the scale turn off already?
No.
Okay, let's do it. What do you think it's going to be?
Bad.
Let's see. 10 corresponds to 1.
It just shut up.
Okay. Well, now I got to be extra careful because I got to make sure I do it when it's not in tension, right? Okay. What do you read?
1 kilogram.
1 kilogram. So if I could go up here, zoom in. Oops. Right, you can see, and of course the light's so dim you can't read it. It's about 1 kilogram there. You see that? So it'll show up on the video, but that reads 1 kilogram. So why is this? Some students get confused by this. So I've got another thing to show you here. I don't think you'd have any trouble thinking it in this way. If you hang something to the ceiling and acceleration is equal to 0, right, and the weight is the 10 Newton weight, you have no trouble thinking this should read 10 Newtons. If we go over here to this one, if I just wrote this over to a wall, well, you'd think, well, it's still being supported by that cable. It's 10 Newtons because acceleration is equal to 0. Now, if we go to this extreme case, the acceleration is still equal to 0. You can think of everything over here as being mathematically equivalent to the wall, right? It's a little bit weird. It's effectively a wall. And in this case, if this was not accelerating, if this is not accelerating, the tension in the cable should read 10 Newtons. So what does a scale read? It reads the tension. I'm just trying to prove this to you. The tension is what this reads. Imagine this was one cable all the way, right? There's 10 Newtons up here, there's 10 Newtons here. It's reading the tension in line. This might get trickier if things were accelerating, but we'll worry about that case some other time. So far, so good with that?
Yeah.
Just a little fun brain teaser. Take a look at 5.6.
One weight is heavier than the other.
If one weight is heavier than the other, problem 5.29. We'll do it in a week or next week. It would accelerate. Do you agree? And then the tensions would not necessarily equal the weight. Are you okay with that, Peter? If the one weight is different, or if one mass is different, yeah. Okay, when you look at 5.6, that makes me think of that. No, you're good. And then it's a little hard to read. Let me zoom out here a little bit. Okay. I'm going to change the EV down a little. Okay, so in this case, take a look what we got here. We've got a scale here. It's got a tension, and we're going to get an angle. We'll write down the numbers in a minute. We've got a scale here that's got a tension and a different angle. And then my question is, basically, this scale is going to read the tension in this bottom cable. To be clear, in this special instance, what is the acceleration of this hanging mass right now? 0. Do you agree that this scale reading will correspond to the weight of that? In this special case, yeah, we could say the tension is the weight. Do you agree? Because A equals 0. So basically, my question is, what mass did I hang on there? What's the weight that I hung on there? Got it? Okay, let's set up the problem. Okay, I'm going to try and do it. You can write it out yourself. You can work with your neighbor as fast as you want. Has most of this been kind of review tonight for everybody?
Yes.
And maybe like a couple things you're like, oh, whoops, I forgot about that. Hopefully, getting back into it pretty easy. Most people like this part, so just remember this too, right? You got this horrible lab tomorrow, you're gonna have that over soon. You got the exam one, which is usually pretty hard for people. And then we'll at least have a short period of time where we're doing something you like and maybe are familiar with. So there is a little bit of a respite coming. Okay. This problem, there's a washer. Let me get back here. Oh, there we are. There's a force kind of at the steep angle. I'm going to label that T1. We're going to record this angle as phi. And there's this one off at some other angle. And this angle over here is theta. And then in this particular problem, strictly speaking, this should be T3 going down, right? But do you agree in this special problem, we could replace T3 with mg for this particular problem? All right. And just so we know, I'm going to go read those numbers again. Oops. Give me a second. Jeez. Come on, EV. There. Okay, so tension 1 looks like it's basically right at 10. And then the angle, we're supposed to do this angle, 44. So 10.0 and 44. I'm going to write this down. 10.0 newtons. Phi was, what did I say, 44 degrees? Okay. Other one, I'm reading it carefully. I think I read 8.45. And then the angle is going to be 10, 20, 30, 40, 56. 8.45 and 56. Okay. Okay. Now, basically, we're doing a variation on this problem, and then I'll pick up the extra parts at the end. I want to have some fun, and I want to actually calculate mg. All right? I want to figure out what this should be, and then we can lift this and see if we're right. Gee, I wonder what it is. It looks exactly like every other 1 kilogram mass. We've been using it all day. I don't know. It's such a mystery. Okay. In this case, what is the acceleration in this problem? 0. Okay, so that's convenient. A is equal to 0, right? All right, so in this case, we need some force equations. Well, do you agree not all of our forces line up on the coordinate system? So we must split into components. Usually people do it this way when they're first started. What's this angle right here? Phi, whatever, interior, whatever. Technical geometry there. What is this side of the triangle? I guess we could call this T1x, and this side is T1y. Help me out. Should I use SO, CA, or TOA to relate T1x to the magnitude of this side, T1? Cosine. So we'll say cosine of phi. Whoops, I'm off, aren't I? All right. Is what? What? So CA, TOA, adjacent is T1x over hypotenuse is. So out of all this, we get T1x equals T1 cosine theta. Is everybody okay with that? Right? Cosine of this. Now, to be clear, this gets old. We don't want to do SOHCAHTOA every time. So what I like to do is just, this is how I think it through. We could do all this, and this is all absolutely correct. I think I might have miswrote in the last line. Did I write theta? I did. Oh, crap. Good thing we erased it. So that was almost correct. Here's the way I like to think about it. This side's adjacent. It relates to cosine. So this is T1 cosine of phi. This side is opposite phi, so it's T1 sine of phi. Make sure you're good at keeping track. We've got thetas and phis in most problems here. Got to keep track. Based off that, I know this side has magnitude T2. What's a good way to write this side?
Sine theta.
T2 sine theta. I'm not trying to do this to hurt you, right? Normally you're like, I feel so uncomfortable. An x component has a sine in it. In the real world, sometimes angles to the vertical make sense, or they happen to be what was measured, so we use them. What's this side?
T2 cosine theta.
So far, so good? What are some force equations? Somebody tell me, how about the forces in the x? What are they? Is that going to be plus or negative in this particular coordinate system? Negative, excellent. It's negative because the coordinate system says this way is positive, that points the other way. Next. And I'm going to do one extra step. You're absolutely correct. I'm just going to write it like that just in case. So the idea is if this was accelerating, the same procedure would apply. It's just this wouldn't go to zero. Absolutely. Outstanding. Okay. Ratio. What's some forces in the line?
T1 sine phi plus T2 cosine theta minus mg.
Okay. You're on it, Alan. Thanks, boss. What's AY?
0.
Feeling good? Hey, do we have enough information to figure out mg? Do it. mg equals some crap. I'm going to move it to the other side. What do we get? Did I screw that up? If I move mg to this side, these don't change. Then I flip the sides. Again, I move mg to this side, and then I just flip the sides.
I have a question. Why would it be negative T2 cosine theta?
Did I screw up?
Yeah.
I did. You're right. I'm wrong. You agree?
Well, it would be negative for the.
It should be negative for mg. Agreed?
Wait, no, never mind. I
No, you are absolutely right. I was wrong. Let's look at it and see why. T1 sine phi is up. T2 cos phi is up, and both of those are supposed to be up. So you are right. I was wrong. Good?
Yeah.
Outstanding.
No, it's just I derped up on the math later on.
Yeah. We would have caught it later when we checked. It might be like, the mass is not -6. Or something like that, right? Okay, we would have got an incorrect mass and we would have looked and we would have found that. Outstanding. Hey, let's punch in the numbers. You guys are fast. Remember that this together is the weight, right? That's what the scale reading should be related to because acceleration is 0. Punch it in. Check your calculator, make sure you're in Green's mode. I'm trying to make a force problem slightly interesting by giving it a puzzle. I hope you appreciate that. If not, apologies. I find it slightly more fun if it's connected to reality. Anybody punch it in yet?
Yep, got it.
What did you get?
I got 11.67.
11.67. I wonder if that's right or not. Now, in this problem, how about we round this? It's approximately, this scale is really hard to read, 11.7 newtons or about 12 newtons. Agreed? Huh. I told you it was 1 kilogram, and this reads 10. Do you agree? Let me put the zoom over there. Hold on a sec. You're faster than me because I got to deal with this, right? Oh, I like those flowers. That's cute. My kids would be so happy. All right, whatever. Oh my gosh, so painful. I have to manually adjust the iris. That's what I'm doing here so that the numbers actually show up on the video. And I guess I better zoom out a little bit. Okay. Yeah, so this reads 10. We said it's supposed to be a little over 11. What were you saying?
The mass of the pulleys.
The pulleys, these things? Not, that's not it.
The mass of the scale?
The mass of the scale itself, about 150 grams. Do you agree that the scale is not reading its own mass? How much should that shift the numbers? Well, let's go back essentially to here. I'm gonna do this. Right? The idea is our mass total that's causing the downwards tension is not the scale reading. It's the scale reading plus the weight of the scale. So mass total is 1.0 kilograms for the hanging mass plus 0.15 for the scale itself. And when you add those together, what do you get? And multiply by 9.8. That's 1.15 kilograms. And then we're multiplying that by 9.8 meters per second squared. What do we get when you punch those in real quick? 11 point what? Pretty close to that. That's not exact, right? Shouldn't it be a little bit less than 11.5? So 11.3. Now, there's always some slop, especially when I'm involved taking measurements. But I hope you agree this is pretty good agreement, right? You could do a percent difference. What's 11.3 minus 11.7 is our experimental, oh wait, 11.7 is our theoretical result, right? So 11.3, it's experiment minus theory. All of it theoretical. I don't know which one you want to call experiment theory, it doesn't matter. What do you get for a percent difference? About 4, right? Maybe 3.5. What percent do you get? What is it? 3.4% or about 3% negative. Meaning this value is less than that value. 3%, that's pretty good for a physics demo, especially when you consider these scales are pretty crappy. I'll show you one last thing. This is always a fun feature of these scales, right? Whoops. Oh, humbly, holy, holy. You can literally just. Oh, now it reads 4. So these scales are kind of janky. That's what I'm saying. I think 3% is pretty reasonable when you consider the calibration for these scales is pretty screwball. You just kind of calibrate it by hand. And you're like, oh, that looks like about 10. Looks great. Isn't that absurd? So yeah, now once the scale is set to a value, it works pretty well. But basically, you're resetting the 0 value every time you touch the scale. So you have to reset the 0 every time. So to think that I got this thing calibrated right, you know me, I'm like throwing stuff all over the room. All right, doing good on this one? You guys enjoy having some numbers or not? Yeah, all right. Now I have another question for you. let's look back at this question and see. Okay. I'm looking at part D. There's two physics tricks I want to teach you, right? You're probably tired, but I know two tricks that sometimes are useful just in case you haven't seen these tricks. I'm going to rewrite the force equations that we have over here. I'm just going to rewrite them this way. T2 sine theta should equal T1 cosine of phi. This is from the sum of forces in the x equals mass times acceleration in the x, which was 0. Notice the rights equal the lefts. You agree with that? From the equation we had before, you could rearrange it. The rights equal the lefts. Whoops. All right, basically taking these equations and rearranging them. I'm going to do the same thing with this one here and make the ups equal the downs. Actually, no, I'm not. I'm going to solve for T2 cosine theta just for no good reason. You could say the ups equal the downs. That would work. I think when I rearrange these, I get mg minus T1 sine phi. Is that correct? Did I flip something? Double check your equation. Does that look good? Did I move it around right? Good. Okay, thanks. Okay, part D says eliminate T2, solve for theta. Elim T2, solve for theta. What's a cool trick to do this quickly? How would you do this? Or how would it give me any method to do it? Arc sine is not the best way to go.
Oh, sorry. Divide by sine theta. Oh, you can't do that.
Okay, well, you want to divide by sine theta.
You could do that, but
Then what would you do?
you're gonna have a tangent thing.
Okay, well, let me ask you this. Basically, aren't you isolating T2 and then you could plug it into the other equation? That works. Although there's a faster way. You're going to hear me say this a lot. Alan, do you know what I'm going to say? Do you know what I'm going to say? Oh, what do I usually say here? What would Horatio do? Remember, I don't know. Maybe he has to put up with me. Either that or he's bored out of his freaking mind. Alan's like so good at this, it's ridiculous. I like to say, what would Horatio do? Horatio, an arbitrary person that doesn't exist, would take a ratio, all right? So if you ever hear me say that, that's what I mean. Okay, if we take a ratio, what happens on this side? T2 is eliminated, which is what you were saying. What do you get left over? Say it. Tangent. Sine over cosine gives me tangent theta equals. Now it's not pretty. Physics doesn't have to be pretty. It just has to be correct. Done, right? I got to take a tan inverse. So if you want, you can say, oh, I don't want to write all that. I'll just skip right to. I don't recommend that, but because I'm on Zoom and I know I'm going to run out of whiteboard space, I'm going to do that. Again, you take the ratio, you get tangent, you do tan inverse. That's a cool trick. Everybody got that? All right, should I cancel the T1s? Gesundheit. We're going to go like this. Check this out. You don't have to cancel the T1s. And in fact, we can't just cancel them. But anything I do to one term, I could do to every term like this. You might be saying, dude, that's stupid. Why would you ever do that? Give me a second. You agree when I do that? When I rewrite this, I get cosine phi sine phi mg over T1. If you had to code this, it technically uses, I think, one less call. So you're slightly more efficient in a computer program. Maybe that's going to help you get the next Google. I seriously doubt it. But there's another reason this is nice. What should you do with your final answers? Check the units. Very good. What should be the units of an angle? Radians, unitless. We don't say degrees. Good job. This is a function. Functions are unitless or not unitless? Unitless, right? You don't see units popping out on your calculator when you hit an inverse, right? Okay. What about the argument of functions? See what I mean about chapter 1 being useful? What is true about the argument of this function? Units or no units? No units. Functions have no units. Arguments of functions have no units. Good. What about this? Units or no units? No units. It's a function. What about this? What about this? This is, yeah, newtons over newtons. It's actually a little bit easier to check the units in this way. So anyways, so far so good. If you wrote this on test day without the divide by T1 or this, I'm super happy. Okay, cool with that? What would Horatio do? Take a ratio. Now, somebody asked earlier, why would I think to do this? Generally speaking, I would say it like this. How would you know to use this trick, right? Just because you know a trick doesn't mean you'll know when to use it. Look, this was our original scenario. If we're talking about this vector, and I say, can you help me figure out this angle? That's a sign that we might want to use that trick. When we're talking about these vectors, this is such a common trick. If you're looking for an angle, consider isolating these two terms in the FBD, taking a ratio, eliminating the magnitude, and looking for the angle that way. It's an old school physics trick. Everybody cool with that? This is when you might use it, and it can save you some time. Good enough? Read the next part. Oh, question.
Question. Why wouldn't it work if you were to just divide that by algebra?
It would, but it might take you longer.
Okay, I see.
Yeah, it's not. So I think if I understood your question right, you're saying, couldn't I just divide by sine theta and then plug it in?
Yeah.
You bet. But like everyone hates physics so much, saving one line, you get used to it. Yeah. So yeah, that's it, right? It just saves mathematical manipulation. And here's the other thing. When you start having to move things around, you might not see it at first. And the more you have to move things around, that's the more chances you might screw up. The less stuff you have to screw up, the more likely you are to pass the test. Cool? So the fewer algebra steps you have to take, the fewer mistakes you might make. With a cake, in a lake. With a shrike? What is a shrike? Isn't that an organism? Whatever. Isn't that like an evil death bird or something?
A drake?
Oh, I like that. A mandrake? Oh man, this guy's a flake. I better stop. Don't get me started on palindromes. We'll be here all night. Okay. I really want to start saying palindromes, but we gotta focus. All right. Let's get back to this. Look at part E. That was part D. Great. You guys are awesome. Cool. Whatever. P2. Let's go to part E. In part E, we're going to switch this up. Sometimes you don't care about the angle, you just want to know how much force to apply. Oops, I used the wrong color. So in the last problem, maybe we don't care about the force magnitude, we just don't know which way we got to pull. There's a time for that. Now, maybe there's another scenario you could imagine. I want to get the magnitude that I could care less about the angle. Any ideas how you can approach that? Any ideas? Anything you maybe wrote on your paper that we discussed a few minutes ago?
Oh,
Yeah, you recognize it? You see it?
right.
Anybody see the trick? I happened to be talking to him about this earlier. I was curious if you remember. I want to get rid of the angle. I'm just going to show you.
Oh, magnitude.
Okay,
Compare magnitude to-
this might not be obvious to everybody. I'm going to take everything on this side and square it. That means I got to take everything on that side and square it. Why is that a good idea?
So, there's a, what do you call the sine and cosine?
Some trig identity.
Yeah.
What's the trig identity that you're shooting for here?
Sine squared, cosine squared.
Sine squared plus cosine squared. You see it?
Yeah.
We're gonna get, that's the trick. Now, because I'm lazy, and I know this is written down for you, it's like students hate this. I'm gonna erase this and just write it like that. Do you agree that's the same thing? It just saves me about a half hour work. You cool with that? What are we gonna do? We're gonna add these now. What do you get on this side? There's a T2 squared sine squared theta plus a T2 squared cosine squared theta. Then over here, we got a bunch of crap. So what? Doesn't have to look pretty, it needs to be correct. People try to make everything look pretty all the time. That's nice, especially in a presentation. But sometimes equations are just heinous. Now, what can I do right here? Factor it out, right? Isn't that a cool trick? Do you agree that's what you were just doing a minute ago?
Yeah.
I knew you would too. It's because it looks a little different. But
Yeah.
now you see that trick,
Squared, but
there's a
all that.
reason I make you do all these horrible tricks in this class. It's because they're used at random points throughout various engineering and physics classes. A lot of times you're like, why is he making me do this stupid problem? It's because I've done a lot of classes. I know the types of math that you're going to need for certain problems down the road. And I'm all about trying to give you an edge. As crazy as it may sound, I'm trying to help you by this. I'm not trying to demoralize you. It's just a natural byproduct. Right? But if you could just hang in there, do you agree we get a bunch of words here, a bunch of crap? And then at the end, do you agree T2 is going to equal the square root of a bunch of crap? You could get that. Should I use the plus or the minus root? What does T2 mean? Is it the force of tension 2? It's the magnitude of it.
That's plus.
Got it? Nice job. What do you think? Ready for another half hour of fun? Oh my gosh, this late class, it's like, man, I don't know how you guys do it. I appreciate your ability to stay awake. Thank you.
It's just cold showers.
That's right. Oh, you want me to get some ice and we'll get the Gatorade plunge? Ah!
I'm
Anybody
ready
fall-
for it, actually.
Yeah, right. Okay. What was the goal of this? In parts D and E, I'm just showing you some standard math tricks for moving symbols around. Cool with that?
Yeah.
All right. Take a look at 5.7. 5.7 really quick. I'm going to erase the board. Take a look at 5.7. Work at the car wash after this. Oh, man. Holy cow. Oh, question? Oh, wax on, wax off? Yeah, yeah. I'm ready. Ralph Macchio got nothing on me, man. All right, so one more weird way. This video is horrible. All right, let's say you got a hanging mass on a string. You got a string. Maybe it's connected to a wall here. Connected to a wall here. We're gonna put a little mass on here. Okay. What forces act on the mass? Give me one force that acts on it. mg straight down, got it. Is there another force acting on it?
Tension.
Tension. Which way? Show me with your fingers. I like to think tension always points along the string. Well, I would say this way and this way. Now, do you agree the net effect of these two would be upwards? The net effect of the tension is upwards, supporting it. In particular, I think in this problem, wasn't there an angle here? Did I call it theta or phi?
Phi.
Phi? All right. So this is phi. What's this angle right here that I'm pointing at?
Phi.
That's also phi. What's this side right here that I'm pointing at? T cos or T sine phi?
T cos.
Jason, got it? You agree there's a T cosine phi this way? Oops, and maybe I'll label it like this, just so I could see this. Do you agree it's the same string? So if you have a single string, one of the main differences, notice I'm not putting T1 and T2 here. Did you see that? Okay. Linda.
I didn't bring my key, so I can't get into the stock room, so I'm
Gotcha.
cutting. Sorry, I didn't mean to.
I don't care. All right. Now I have a question for you. I've seen this on many a test. I've seen students say, well, it's sitting on the string, there must be a normal force. What do you think? Is that true or not true? This is confusing, right? You're like, well, it's technically pressing against there. Isn't the net effect of the tension, and this is where I was going with Alonzo. Do you agree these two components cancel, the left rights? The net effect is these two components upwards, which act like a normal force. But effectively, it's the tension in the string that's holding it up. We don't draw a normal force. Got it? Just wanted to let you know that. In particular, what's this force equation give us? What's the vertical force equation? Let's assume it's at rest and not accelerating. We'll use a standard coordinate system. We'll say A equals 0.
T sine phi.
The ups equal the downs, so 2t sine phi is the up force. Minus what? Or minus mg or equals mg, however you want to say it. Is everybody okay with this?
Yeah.
This is the ups equal the downs, because A equals 0. Do you agree? I can't always do this. Only when A equals 0 can you say the ups equal the downs. Cool? Give me the tension. Two sine phi. Make sure I didn't screw that up. Looking good? So far, so good?
Yep.
What practical application does this problem have? Can you think of anything that has a wire that looks like this There's kind of a small angle here and something hanging on it.
Those track.
I was gonna say clothesline. Maybe it relates to a bridge as well. Think about this.
When people go,
Well, let's stick with clothesline for a minute, because that's where I want to go, and we can do that too, right? You can imagine somebody walking on a tightrope as well. Agreed?
oh,
This
that's
could
what
be
I
the
was going
person.
with.
Is that where you were going?
Yeah.
Same concept, clothesline tightrope. What should happen to the force if we use basically a smaller angle? So let's say we don't give as much slack so that the angle gets smaller. What happens to sine of phi if phi goes towards 0? Remind me, what is sine of 0? 0. So as the angle goes to 0, what happens to this function? Sine goes towards 0. What happens to the tension? It blows up. Right? What happens if you get a lot of tension? If you hang too much wet laundry on your clothesline, the bolts rip out of the wall because the tension's too high, or the cable snaps. Right? That's a practical application of this. So if you try to put too much tension on there, you're just going to destroy the clothesline. Either the cable or the bolts affixing it. Ooh. Look at this. We destroyed this marker. That's cool.
So is it better to have more slack?
What's that?
Is it better to have more slack?
It's tricky. You don't want your clothes dragging in the dirt. So you got to have a trade-off. And so the clothesline, you don't necessarily want to use a skinny little string. You might use a steel cable because you know there's got to be some tension in it. When you put all that laundry on there, it's going to blow up. You got this small angle that's going to amplify the weight of the clothes in this weird manner. Here's another example. Take a look at this. Oh, let's just erase this and do it right here. I erase it. What would I do with it? There we go. Let me give you another example. All right. What if you're very creative and you send a micro drone into somebody's mouth and you do a downward looking view of their teeth? So this is a strange organism that only has what, like 7 teeth? So what? If you've never seen an x-ray of a child's mouth, it's freaky.
Oh.
Check it out. They're like, you know, they look like goblet fish. Anyways, these are teeth. Top view of teeth. What's something that we might put on these teeth? Braces, brackets. Now think about this. Okay, there's more than. This is orthodontia physics. There's usually a wire that runs through the brackets like this. Now in this case, if I just look at this one tooth, there's going to be a tension this way and a tension this way, and the net effect is going to push the tooth back into alignment. Now think, what do we know about this problem? There's skinny little angles, right? Because think about this, adjacent teeth, there's going to be a very small theta. What's going to have to be true about that tension? Big or small if you have a small angle? Big. So you need nuclear cement to get these brackets on, and that's why kids are always popping their brackets on. The parents love it because orthodontia is never covered and it's really, really expensive. So if you got braces as a kid, thank your parents. Okay, it's like it hurt them badly. Hurt them badly. Anyways, yeah, unless they were lucky enough to have insurance that covers it. But yeah. Gee, I wonder what I'm thinking about with my children. Paying for their orthodontia, $5 grand a kid. It's not gonna be cheap. Maybe more these days. That's what I'll do. I'm kidding. Let me know if somebody will go down there for vacation. Come back. The teeth will be good, right? All right, ready for another problem? All right. I need some kind of a zombie problem. Let's try the next one, page 86, 5.9. I need zombies. Five point nine. when you're drawing this picture, draw it big. If you're writing notes, we need a big picture for this one. We're gonna do a lot of extra stuff, okay? Keep it big, all the way across. For this problem, it's all about geometry, and that means we got to label crap. Now, in this problem, we're told there's a zombie pulling a suitcase at some weird angle, some magnitude t, at some angle relative to the plane phi. Okay, the angle of the incline itself is theta. Right, so there's basically a zombie pulling a suitcase up the back of a U-Haul. Gonna load this suitcase in there because you know zombies love to do that. We are told what other information? Constant speed up the ramp. Speed is v, not v. Do you agree? It's v without the vector, constant v up the ramp. In this case, we have constant speed in 1D motion. Do you agree that's the same thing as constant velocity? In this case, constant speed in one direction is also constant velocity. Agreed? Constant speed is not always constant velocity. All right? We'll discuss that more in later chapter. But if you have constant velocity, what else is true? Sweet. And then was friction negligible here? Yeah. Sweet. Friction is negligible. Next, we're trying to analyze this block, and probably we're supposed to do an FBD or something, right? Is there anything else? Oh, the mass of the suitcase is M. Maybe I'll label that. Okay. What's one force acting on it? mg, which way does that point? Straight down. Now I'm going to be doing something that Dom's going to be questioning me about, but I'm doing it for a reason. Technically, I'm not drawing an FBD. Do you know why? What does FBD mean? Do you remember the words? Free body diagram. If you have a free body diagram, you're supposed to draw only the body of interest and nothing else, including no rail. But for this first time, we're going to draw two diagrams, one that's not quite an FBD, and then we'll redraw the FBD. Trust me. I know what I'm talking about. mg, any other forces? Normal. Which way does normal point? Perpendicular to the plane, right? Here's the, right? It's perpendicular to the plane. Sorry if you can't see that. All right. Oh, I guess I'm gonna have to use this one. Happy now, Don? Whatever you want. Yeah, I know, right? Okay, here's the thing. I have two things I want to teach you right now. Students screw up this diagram a lot. What students oftentimes do is they'll try and rotate it and then draw it like, oh, in high school, my teacher said, just put the block here, and they'll say, I'm going to draw the block flat and draw the forces. Okay, technically you could do that. It's bad practice. As the problems get harder, it gets harder and harder to do this with multiple block systems, and pretty soon you will screw up. Don't do it. Bad monkey. It's not that it was wrong. It's just that it's bad practice for what we are going to do and take this further. Okay? It was totally correct. It's just not a good idea with where we're going. Enough said. Another thing, students will draw angles that look like crap. They will draw stuff that's on students, the natural tendency of a student, anything that's angled, they draw it at 45 degrees. I don't know why, but I've seen it a million frickin' times. Do me this one favor, and it will save you a lot of headaches and a lot of geometry. Draw the angle skinny, or draw it big. Just don't draw it at a 45. Okay, I call this the skinny angle trick. Copyright. Okay. whatever, trademark, I don't know what you say, I don't care either. Watch this trick. What's this angle right here that I'm pointing at? 90. What's the sum of the angles inside a triangle? Do you agree that theta plus alpha plus 90 should equal 180? Well, said another way, can't I just subtract this off and say that alpha is equal to what? 90 minus theta. If you have a right triangle, there's a trick. This takes up 90 degrees. If this is theta, the other one must be 90 minus theta. Is everybody okay with that angle?
Yep.
Okay. Next, I'm going to make another right triangle. Right there. Oh, sorry, another right angle. I think I said triangle. I apologize. Look at this in here. And I'm going to try and make this look a little bit better. This right here is a right angle. Do you see it? I'm trying to draw it as a right angle. I apologize if it's not. I'm a little off center. That's a little off. Do you agree? Let's fix that up. I gotta stand here just so I can see it. That looks a little better. This is a right angle right here. What's left for here? If this is 90 minus theta, and this whole thing is 90 degrees, what must be inside here? Theta. I ate theta. So far, so good? Now, do you agree we could solve this problem with a normal coordinate system like this? X, Y. We could draw some forces and split stuff into coordinates. However, do you see that this one is already lined up on the rotated coordinate system? And in fact, I don't want to have to use trig identities where I'm using theta plus phi all the time. Ugh. We want to avoid trig identities when possible. Exception, sine theta over cosine theta equals tan theta, sine squared plus cosine equals 1. So what I'm going to do is I'm going to get spicy. I'm going to call this the x direction, and this the y direction. And in this particular problem, we said a is equal to 0, right? So far, so good? Why is this advantageous? Do you agree that the n vector and the t vector are pretty straightforward to split up on this coordinate system? There's a component parallel to the plane, a component perpendicular to the plane. This side is going to be what? T sine or T cos? In this case, it's T sine. This is
T cos.
These three are done. Now all we have left is this one. Now, I know you're tired. I know you don't want to pay attention. I know you want to run out of here and do a kickstand. But before you do that, watch what I do right now. I know you're tired. Everybody give me your eyes. Even if you're writing, stop. It's important. Here we go. I'm going to split this into components, right? What do you think of that? Good or bad? Bad. You see a right triangle, but this is totally wrong. The vector itself needs to be the hypotenuse of your right triangle. This is invalid. Look at this. Did that line, look at this line. Does this line match my coordinate system?
No.
So it's not working. You need to draw a component this way.
Or at least make it parallel.
Exactly. So let's try and fix this up like that. See the difference there? Notice the right triangle is opposite the original vector. Sorry, I keep saying right triangle. The right angle is opposite this vector.
Yeah.
Now I know this side is mg. What's this side?
mg cosine theta.
What? Oh, yes, good. Okay, good. mg cos. What's this side?
mg sine theta.
Yeah, and now I guess I'll just use this because I'm lazy. What do you think about that? Does that make sense? Why you split up these inclines like this? why do your teachers do this to you? Why do we do all these boring blocks on a plane? It turns out the math for blocks on a plane looks a lot like blocks spinning in a circle on a string. You may not see it right away, but this trick of having a coordinate system that changes will help us understand much harder problems that are moving related to machines that actually make life better for humans on Earth. So hopefully this technique, I don't know what it is. How are people feeling on, do you understand how to get to theta? Did that make any sense? Thumbs up, thumbs down. All right. Now let's draw our FBD. We kind of know what it looks like. This is just so messy, it's not worth working with this. Let's redraw it over here, and then it truly is a free body diagram. Got NG. I'll get out of the way in a minute. Got a normal force. I kind of have to do this online or I get crooked. There's other ways to do this. This is not the be all end all, but this will match the solutions that I write. And I'm confident in your abilities to do what other teachers want. Don likes things a little bit differently. He moves some vectors around a little bit. But if you can do this and get used to the habit of drawing a coordinate system separate, drawing the vectors, labeling them, and then when we get to chapter 10, we put this on steroids. In chapter 12, we really go nuts. I think you'll be in a position where it should be fairly easy to adopt to an engineering style if you're in engineering. Okay, so you just gotta believe me here. What's this? I'm already getting tired.
MG sine theta.
Thank you. Like that. Is there anything else? Did I forget anything? Oh, this was phi. Yep. That is a free body diagram. I've got the object by itself with the forces labeled. I've got a coordinate system. I've noted the acceleration. That helps me grade your work on the test. If you write your free body diagram, this is test 2 now we're talking about, remember? When you get to this subject, right, on your test, there's usually going to be some problem worth 9 points, or maybe even 11. And it'll be, can you draw the free body diagram right? Can you get the force equations right? And then can you solve for something? Actually, I think it's 7, but whatever. It's like 4 points for the diagram and the force equations. 3 points for doing the algebra right. More points for getting this right. Cool? All right. From there, you can do whatever you want. You could solve for something. Now, we're almost out of time. I have a bonus question for you. Right? Getting the force equations from here is, we should do this. Let's get the force equations. Do you agree we should double check? Take a second and write them down. I'm tired. I don't want to do it, but we should do it. Broken by Zoom. Give myself a little extra room. In this case, anybody feeling brave? You want to come? Oh yeah, do it yourself. I'll do it myself. We'll check at the end. Everybody do it. I'm tired. You can do these steps. You're going to be good. Are there any other forces in the x direction here? Are there any other arrows parallel to the x-axis?
Mine is MG sine theta.
Minus mg, opposite, opposite, opposite. Nice job. Always important to keep those thetas and ph's looking different. Is there anything else left, right? No, 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 we're good, right? So this is all equal to what? In general, what do we say? Mass, A, and then in this particular case, what's AX?
0. So I say 0.
Yeah. But the thing is sometimes it might have an AX, but not an AY. So I'm trying to get you in that habit of always just think carefully. AX and AY could be different values. This one, somebody read it out to me. What are we gonna get in the y direction?
T sine phi minus mg cosine theta plus n.
T sine B, you said what? Minus mg cos?
Yep, theta.
Thank you.
And don't forget the normal force,
Plus-
which is plus n.
Still on, Alan? Alan?
Yeah.
Whoops, not AX, A, Y. It's like just barely in there, right?
Yeah.
All right. Oops, that goes to 0. Whatever. What do you think? Okay, this has got to be your bread and butter. You like this stuff more than projectiles and stuff?
Sure.
Or at least does it feel more familiar?
Yeah.
Okay, so you've got to get through chapter 1 and 3. You've got to do chapter 2 like crazy. You've got to do chapter 4. Right? And you got to ace that on the test. And then after that, we're going to be basically doing applications of that stuff with perpetuity applications of it. All right, one last puzzle for you. All right. Look at problem 5.12. Going back to this silly looking thing. Oops. All right. So it's the same scale question, except a variation on it. So imagine we had this thing sitting here like this. Have those hanging masses. I'm not going to turn on the scale right now because it turns out this doesn't work very well. Oh, let's do it. I'll turn the scale on when there's no tension. I know you can't read it very well. The question is, if you're pushing the masses instead of just letting them hang there, is the scale still going to read 10 newtons? What do you think? These are both equal masses. During the time while I'm pushing it, will it still read 10 newtons? What do you think? In particular, let's think about just one mass that's hanging here. Imagine this mass is just hanging here, right? If I push this, is it accelerating? Yes, during the push, it accelerates. While it's accelerating, is tension equal to mg? No. So will the scale still read 10? No. After I push it, let's assume after I push it, it's moving with constant velocity. It's moving. Will the scale still read 10 or will it read something else? What's the acceleration after I'm done pushing it? 0. It's moving, but acceleration is 0. If acceleration is 0, what's the tension in the string? mg. So then it would read 10. And unfortunately, I've only got 1 inch of travel, so it's not going to work out. And I tried to do it earlier, and there was too much friction, and it didn't work very well. So anyways, all right, let's get out of here now. Oh my gosh, I'm tired. Thank you to all those that did the demos today. Appreciate it. Thanks for staying awake. Oh. Brutal, right?